So we talked a little bit about some electrical components, right? A basic control system and then control devices. I'm sure all y'all okay on push buttons. If y'all don't know the symbols, push buttons, switches are okay there. Everybody okay on analog and digital? Are we okay? Don't understand that. So what's the difference? Say you're okay and then you shake your head. Sometimes I think y'all are. I found out a long time ago, usually the person that sits and does this the whole class with people don't have any idea. Used to you think I'm doing a good job, and now you're saying, the guy sitting right here said, I have no idea what he's talking about. I don't want him to know I'm dumb. Well, I'm not dumb. Don't know. I did record it, by the way. Go ahead. Here. Limit switches are not analog. Limit switches are digital.
Digital?
Yes.
Limit switches. Okay. I thought it was just off or on.
No, that's digital. Off and on is digital.
Oh, yeah. Oh, well. See,
Off and on are digital. So don't get mechanical. Don't get mechanical confused with analog. So these light switches over here, are they analog or are they digital? The lights are either on or they're off. When you take a light switch and hook something on it, instead of me going over there and hitting that with my arm, I could rearrange that so when you walk in, you could flip it, and when you walk out, a wire hits you and it flips it the other way, then that would be a limit switch. So that's all a limit switch is. It's just a switch, right? You understand? But normally it's controlled by devices instead of by humans, like a light switch. So what's the difference between analog and what's the difference between digital? Huh? No, that's servo, non-servo, or open loop, closed loop. What's the difference between analog? We can have analog systems, or we can have digital systems that utilize feedback, or closed loop systems. So what's the difference between analog and what's the difference between digital?
Present.
Huh?
Present.
Presence sensors are usually digital sensors, but that's not what the difference between analog and digital is. So when I go out and during the day, they say the high today is supposed to be 88 and the low is supposed to be what? Something. Does it go from the low to the high just like that? Okay, how does it go from the low temperature to the high temperature? Gradually. So gradually is a constantly varying quantity. It can vary an infinite number of combinations between the maximum and the minimum. So a pot is analog. It gives me a voltage depending on the position of a knob. That's analog. I can literally, if I was good enough, I could get any voltage between the low voltage and the high voltage. That is analog. So analog varies. Digital don't. Digital is either what? For digital, we use highs and lows. We use true, false. We use yes, no, 0, 1. Those are digital. Analog would be, okay, what temperature is it outside? Right? You understand. What speed is my car going? So how does my speed control, so that's sensor. I'm not doing 90 miles an hour or 0 miles an hour. When I gauge my cruise control, that's a closed loop system. That sensor that senses speed is what? Is it analog or digital? My sensor that senses speed, is it probably analog or is it probably digital? It's probably analog. It's probably got a tach generator or something like that, right? You understand? So temperature is analog. How dark and light it is. You know, when we talk about it outside right now, sometimes the cloud goes over, sometimes it's not. We wake up in the morning, it's gray, then we go through all these different stages of light during the day. Is that analog or is that digital? Analog. So we live in an analog world. There's very few things in nature that varies digital. Digital is discrete states. Usually when we talk about digital, we're talking about two states. It's either there or not there. So a limit switch is either made or not made. That's why. That's digital. All right. All these photo sensors over here, these are all digital sensors. These proximity sensors, all these are digital sensors. They either say it is there, all these presence sensors that we have is digital. Position sensors could be analog or digital, depending on what type of position. Y'all understand the difference between presence and, right, and position. What's the difference?
Well, something's just broke a vein or something that's just in that area.
That's for presence, right?
But position is a specific place.
Not really. If I'm trying to see position, it has, the positions have the ability to vary. Even though football teams, I say a tackle. Well, if you look at that tackle's not in exactly the same place every time. Sometimes they're all over the place, right? They shift your defense. How we'll call it defensive end. Where can that dang defensive end be? So that would be a position. So a position can be anywhere within a certain space, right? You understand? Where a presence would be is either there or not there. So a lot of our sensors over there are presence sensors. They just sense whether either it's there or it's what? Or it's not there. Now there's a bunch of analog sensors over there. It's just that they're not being used in the PLC program. But if we understood those things, we could rewrite and incorporate it sometimes. So this is what they're showing. They're showing a device called a thermocouple. And what is temperature? Is temperature digital or is temperature analog? It's analog. I mean, there's no thing I know that can go from 0 to 100 degrees in no time at all. I've never seen anything that could do that. So that's what they're showing you there. And then, of course, some analog sensors for position. We have potentiometers. So when you take the sensors class, the first lab you're going to do is with a potentiometer. Y'all understand how those things work now. So a potentiometer is basically what we call a variable voltage divider. So back in DC, you learn about a voltage divider. A voltage divider is a series circuit, right? And each resistor drops a voltage proportional to the other resistors in the circuit. Well, a potentiometer is a variable voltage divider. So instead of me having a fixed resistor, so a while ago I said a 5K and a 5K. I'm going to try to get to my markers. They're right on top of so a voltage divider would come up, and a while ago I said, okay, this is 5K and this is 5K. And that would be a fixed voltage divider, right? You'll understand that. And if they were both 5K, then what would be the voltage in the center? I'm listening. No.
I'm throwing numbers out.
Well, don't put, it's going to be 1/2 of whatever I apply. I mean, if I put 10 volts up there, it'd be 5 volts. If I put 12 volts, it would be 6 volts. If I put whatever voltage I put up there, it's going to give me exactly half. But that's what we call a fixed voltage divider. Okay, y'all understand that? But what we do with a pot is we simulate those two resistors. So the pot, we got two options. I can make it act like a straight piece of wire between here and the wiper. Or I can make it act like a power supply, so I could make it act like that if I put it up there. Or I can adjust the ratio of the two resistors. And it always equals to, so the resistance across the pot does not change. So when we talk about a 5K pot, that means across the ends it will measure 5K, depending on the tolerance. It's not going to measure exactly 5K, right? I think the pots that we have are 10%. So it's going to be 5K plus or minus 10%. What varies is where we tap off these two resistors, right? You understand? So what happens if I move it in one direction, if it's let's say 10K, I move it in one direction, this guy here might go up and this guy there here would go down, but the sum of them would always equal to what? 10K. So right now, this guy at the top would be dropping 6/10 of the voltage. This guy at the bottom would be dropping 4/10 if it's a 10K pot. And of course, I'm not going to reduce those, right? And of course, if this right here went to 8K and then this right here was 2K, then the top's going to be dropping 8/10 and the bottom's going to be dropping 2/10 or 1/2. So that's how easy this is, right? You understand that, or 1/5. But what I can do with that pod is I can vary that output voltage between the wiper and one end. So normally what we'll do is we'll come up here and we'll make one end common, and then we'll put a voltage up here, or whatever we want to do. And then I tap off right here. So I take my load would be taken right there. So now what I can do with that pot is the voltage I get out of the pot will be proportional to the position of the pot, of the position of the knob, right? You understand that? So I can very easily take that pod and hook it up to something. Maybe put a weight right there. And then when this over here moves up and down, what does it do? It rotates the pot. The pot would give me a voltage indicating the position. We got some open loop robots over there. And what the guy did is actually put a pod on all the axes. Now he turned a what? An open loop robot into a what? Closed loop robot. And they fed it into that little Arduino processor that we showed y'all the other day, controller, and now they had a closed loop robot. So this is showing you the pod. This is a good animation. This one moves in jerk, but hopefully you can see basically what they're saying is happening. Then we talked about encoders, or encoders are digital. So if I'm going to bring a potentiometer into a computer, what are we going to have to do? Computers are digital. Okay, if I'm going to bring a potentiometer into a computer, what are we going to have to do? Exactly right. So we have these devices called analog to digital converters, ADCs. Now we got different types of ADCs. We got on-off ADCs or digital ADCs, which means we bring an analog input into the thing, and then it either outputs on ours. It's either plus 24 volts or 0 volts. But what we do is we get the ability to set where it switches. We call it the sensitivity. Y'all understand that? And unfortunately, a lot of these things, a lot of times they like to hide these, but sometimes they don't. And this is another big problem with people going out there and doing what? It's in the male mentality. I don't know what it is. Now, we don't go over there and say, I wonder what that switch does. What do? We try it. If I've got something that turns, by George, odds are we're going to do what? We're going to turn it. And unfortunately, that's in our mentality. I don't know what it is. So guys, they don't question they don't say, well, let me find out what that does. We have a tendency to do what? See what it does. We have switches over here on the wall. that basically, and we're going to try to replace them with e-stop buttons. Right now they're switches. So I can go over and I can flip that switch and it kills the power in this lab. But it's a regular light switch. Now it's got this panel on it saying emergency use only, all this other kind of garbage. And by George, the problem is over there in 107, the wireless router or the router for the network is on that circuit. So I'll be at home and I'll come over here and I can't access my network from home. What do you think's probably happened? Somebody's come over and did what? Flip that switch. Flip that switch. Well, where is the switch? What did I do to prevent that from happening? You see that piece of paper hanging on the wall back over there? That's on top of that switch. So all I did to prevent that happening, it hadn't happened, all I did was cover up the switch. So now people can't what? Can't switch it. Because I guarantee you, I could take that sucker off, and within a month, I'd come in here and this whole place would be totally dead. It's happened already. We come in here and nothing was working. And nothing was working. And what did happen? Somebody went over and did what? Put that switch. Now it's a momentary contact switch, but it didn't make any difference. So what we're planning on doing and what we need to do is instead of covering it up, instead of putting a light switch up there, we need to put a what? We want to put an e-stop button up there. So this is what I'm saying. These digital sensors, these are great, but odds are what it senses is analog. So light, is light digital or is light analog? Could be either one. Right, you understand. But normally what we do is the sensor itself is analog, but we run it through a digital A to D converter. And what we do is we set what they call it the sensitivity, but basically it's the threshold of where it switches between a what? Between a true and a false. So every one of these light sensors over there has got a little old tiny screw that if you look real close, you could turn it and change the sensitivity. And let me pause this. All the time. All the time. Unfortunately. These are digital position sensors. We went over those. These are encoders. So I understand those. Are you okay? Incremental encoders and absolute encoders. Y'all know the difference?
Just by the name.
Well, you can't adjust it. It's a position sensor. So look at the difference between the incremental encoder and the absolute encoder. What's the first thing you notice? This is the incremental encoder. This is the absolute encoder. What's the first thing you notice? 5. Now what we're doing with this guy is the computer uses what we call the binary numbering system. Now what is that? And of course, everybody here knows what we call the decimal number system. So binary means 2, decimal means 10. So when we represent numbers in the decimal numbering system, we have 10 combinations that we can use, 0 through 9. So we got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? I don't know where I was watching about when they found some document in India where they detected the first use of the number 0. The computer zeros means something. In binary, we only have 2 states that a digit could have. This is a 0 and a 1. And then we combine this to form numbers, or we can use it to form codes. But this would be an example of a binary number. Now, people that don't know this, they'll look at this and they'll split it up and they'll say 10,101,011, right? That's the way you see it. Now, why do you see it like that? Because that's the numbering system that you've learned all your life. The decimal numbering system is based on 10. So basically, if I write down a decimal number, what did y'all learn this right here? What did y'all call this digit right here? What name did y'all have this? What name did y'all learn for this digit right here? What did y'all call that? Yeah, well, you learned it. I think you call these ones, tens, hundreds, right? Thousands. Isn't that the way y'all learned? Huh? No, you didn't. You called that unit, no matter what it was, you called that ones. Oh, I'm sorry. Yeah, I can understand why that would be. But that digit, yeah, we call that position, we call that position the one position. The one right beside it, we call it what? Tens. The one right beside it, we call it hundreds. And the one beside it, we call it thousands. But that's not, how did it come up with that? Well, the decimal, when we talk about decimal, this establishes the base of an exponent. So this holds a place of 10 to the 0. This holds a place of 10 to the first. This is 10 squared. This would be 10 to the fourth. 10 to the third. Next one would be what? 10 to the fourth, 10 to the fifth. Now, if you multiply 10 to the third, you come up and get 1,000, but they didn't teach it that way. They taught that was the thousands, right? That was the 10,000s. That was the 100,000s. But in real life, each digit holds a weight of the base raised to some power. Now, if I put this radix point right here, which most people call a decimal point, and I put a number right there, that would be 10 to the minus 1. So if I go to the right of the decimal point, we use minus powers of the base, right? You understand? If I go to the left, we use positive powers of the base. Well, binary we call that a base 2 system. So it means all these, I'm going to put 2 up there. This would be 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh. 2 to the 8th, 2 to the 9th, 2 to the 10th. If I put a binary point right there, and I put, this would be 2 to, and I put a digit. What's nice about the binary number is it's either going to be a what, a 1 or a 0. This would be 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, 2 to the minus 4, 2 to the minus 5. And that's the way these work. Now, what's nice about the binary number system is any number raised to the 0 power is 1. And then 2 to the first would be what? 2. 2 squared would be 4. 2 to the third would be 8. So what you do to get the decimal equivalent of a binary number is you just convert the 2's over to the decimal equivalent and add what the 1's are. So if I had this number right here, I'm going to do a real short one. I'm going to write 1, 2, 4, 8. And then I would just add the 1's. So what would this be equal to? This would equal to 11 in base 2. So after a while, but the computers don't understand 9. They understand 1, 0, 0, 1. Right? You understand? And of course, the more digits we add, which in binary we don't call them digits. Anybody know what we call them? Should be lowercase. We call them bits. And then we got what we call bytes. Anybody know what a byte is? That's a group of 8. Right? And then we have what we call a word, which is a group of 16. So we bundle these up. So what I do, we have what we call we have a digital ADD converter, which gives us 2 states when we exceed a threshold. And then we have a binary ADD converter, which means I bring an analog value in it, and it's going to give me a binary number that represents it. Right? You understand? So if I bring a 10 in, it might give us a binary number that represents a what? A 10. And now that I've got it in binary, what can the computer do? The computer can process it with a program, right? You understand? So these guys right here are already in digital. So what this does is this gives me a binary number. So I don't see where it lines up. But somewhere down this line would be a 0. And then when it moves, then we would come over here. So I would have it lined up. And I might have the first one was a 0. And then the next one, I would come over here, and this would be nothing there. And down here, we would have a 1. Then the next one, this would go to a 0, and this would be a 1. Well, this is the way an absolute encoder works. So this has 1, 2, 3, 4 bands. So what I could do is I could do a maximum of 16 positions. So this is what they're showing you. So we start off, I don't know where they start off at. This looks like it's using gray code, and we're not going to get into gray code. But what the absolute encoder does, it gives me a binary number that represents the position. Now, what would be the advantage of that? The advantage of that is if I turn the power off to the system and I come back and turn it on, the absolute encoder would know exactly where the device is at. Y'all follow that? But if you can tell the number of positions, by the way, this is binary, by taking 2 and raising it to the number of bits you have available. So here we got 1, 2, 3, 4. So it's going to be 2 to the 4th. So that would give me 16 positions. If I add another band, I would get 32 positions. If I add another band, I would get 64. 64, right? 128, 256, 512, 1024, 2048. 8,192, 16,384. So that seems impressive, but I've been dealing with a binary number system a long time. So I know my powers of 2s. Pretty good way. It's like that guy, I think it was on Steve Harvey, that's a little, what do they call him? He quoted pi to, I think, 100 digits. Not that he's smart, he just has a good memory, right? The incremental encoder just gives us a series of pulses. Now notice that the 2 sensors are offset. So it has 2 sensors banging. And depending on which direction it's going, depends on which one of them pulses first. So if it's moving in one direction, then this sensor might pulse first. And then this would pulse second, right? You understand if it's moving in this direction. If it moves in that direction, then they would do what? They would shift. So depending on which one of them pulses first would tell me what direction. But how would I know position? I mean, it's no deal to tell direction, but how would I know position? Well, if I was to come over here and count these, so if this was 0, I'd say, okay, this would be a 1, this would be a 2, this would be a 3, this would be a 4, this would be 5, this would be 6. So every time I got a pulse out, I could count. And if I could keep up with the counts, then that would indicate the position. Okay, you understand that? Yes or no? That makes sense?
But I don't see the correlation between those bars, the gray bars, and does it move at all?
Something's going to move. Either what we're measuring, either the scale is fixed and the sensors move, which happens on most dot metric printers, or the sensors move, or the, I say that right? Or the sensors move and the scale is stationary. I say it the same way, but they one of them is going to move and one of them is going to be stationary. Why does it say that at?
Yeah, I just spit it out.
Okay, you said this. Yeah, that's fine. So odds are on your dot metric printer, it uses one of these. And what they'll do is the sensor will be on the print head, and then the band or the stationary. On the robots over there, the sensors are stationary and the band's moving.
We can write down any number.
Any whole number. Fractions, we have a big problem because in fractions, the resolution of fractions is each number can go down to 1/10. What we do in binary, it'd go 1/2, 1/4, 1/16. So if you try to write down a number like 0.6, in binary it's going to be this big. In decimal it's going to be one digit. There are a bunch of binary fractions you cannot. Whole numbers you can represent any number.
Is that something that we're going to really need to know? Yeah. I know in school, is that something you use?
You don't understand this, and you've got a problem with the code. You don't understand this, you don't understand this, you're going to have a problem with counting. If you don't understand that computers are digital, but we live in an analog, so position is not digital, right? You understand? But computers are. What's nice about encoders, a potentiometer would give me an infinite number of combinations. What's going to determine the resolution or the preciseness of a code? On an absolute encoder, it would be the number of bands. So if I've got a certain amount of distance and all I've got is 16 positions, then an absolute encoder, that is it. So let's say the band is this long right here and I got only 16 positions. That means every position would be 1/16 of that space. Right? You understand? So what I have to do is if I want to have a long absolute sensor and get a better resolution, then I have to put more bands. The more band, every band I put, I have to have another sensor. Right? You understand? So if I wanted 65,536 positions, I would have to have 16 bands. And I would have to have 16 sensors. So the absolute encoder, we have to have one sensor per band. And it's going to have a limited range that it can go. Right? You understand? Because sooner or later, this thing's going to roll around. It's either going to hit an end stop, or if it don't hit an end stop, it's going to do what? It's going to roll back around to zero. If it's a rotary encoder. On the incremental band, what we're doing is the resolution would be the spacing between these gray bars. So the closer I can get those gray bars together, the better the resolution of the encoder. That makes sense. But I'm not limited by the number of bands. No matter, all we do here is we just count. But what we have to include with this is we have to include digital circuits that we call counters. And if you have PLCs, you know that one of the things that y'all learn how to set up is a counter. But now all I got to do is do what? Count the stripes. And what determines now is the resolution, or how many counts can those counters go up to. So from 16, which is 65,536, I add one more counter, then I can go up to over, right, 65,000, it's over 1 million counts by using just a 17-bit counter. Now, what's the problem with that? Well, the problem is this: what if I turn the power off my counter? They're digital, they're electronic circuits. For some reason, electronic circuits. So that would be like I go and disconnect my radio from my battery. And you disconnect that sucker back up, what did you lose? You lost every nice little station you had programmed into it. So if I've got electronic counters, which they're digital counters, and you take power off those counters, then what are they going to do? They're going to lose their what? They're going to lose their count. Not even reset it. Literally, if you turn a counter off, a digital counter, and you put power back on it, the count comes up to be what we call random, unless you reset the counter. So you have some type of circuit that would automatically reset the counters if you want to do that. But anyway, the number that you get is a random count. So one option we got is to return this thing to the same spot. So when you turn, anybody got a printer at home? Odds are they use this encoder. When your printer's turned off, you turn it back on. Besides for cleaning the head, you find that sucker is finding itself, right? You hear that thing, and normally what it'll do, it'll have a sensor, usually an optical interrupter, and it'll have a blade on the print head. And what'll happen is it'll just come over and block that blade. A lot of times they send it more counts than it can do, and it'll just stall up against the side, and it finds itself that way. So what we have to do with an incremental counter is we have to start it from a point of origin. Because they use counters. Or what'd you say, Gary? Put a what on? Put a battery on. And then that way, when we turn power off, then they keep their contents as long as the battery don't run down. Okay, so this is what the robots use. The robots use they use these incremental encoders because we're not limited to the range. And what they do is they use rotary incremental encoders. So these suckers can rotate 100,000 times. It don't make any difference as long as your counters are big enough to keep up with the count. The only problem is if I come up here and do what? If I lose power on those same things, then we lost what we call the origin of the robot. And the origin of the robot is out there in free space somewhere. So these are pretty neat. So you can see how the way the slots are lining up here and gives us a different count. But if I turn this guy here off, so we didn't want to do that. Let me do it this way. Then this guy right here does what? He keeps up with the count while the power's off. But the problem is the more resolution, the more bands I've got to do, right? You understand? And for every band, I've got to have a sensor. So this right here is 1, 2, 3, 4, 5, 6 bands. So that would be 64 counts that this thing could keep up with. But as it rolls around, eventually it's going to come back to what? To zero. Used to on automobiles, before they added another digit, is those odometer rolled over it at 100,000 miles. And that was a big deal. Now they've added another digit. So what would it be now? 9 million. They've added a complete number of digits. So we can go to 9 all the way up to the top. So 9,999,000 miles, right? That we could, 999 on our cars now before the odometer, but it would still do what? It would still roll over. And that's what happens with the absolute encoder. So an absolute encoder has a limited range. An incremental encoder does not have a limited range. The only thing that determines the range is how big the counters are. But the problem is if you lose power to those counters, you lose your point of origin. So what does your printer do? Well, your printer finds origin. It finds the left-hand side. And once it finds the left-hand side, then it can keep up with position from then on. If you ever get a paper jam, it gets lost. And eventually it's going to have to refine the origin. And that's the same thing true on those robots. So all these robots have origins on them, but they have what we call an origin, but for the counters, but they're incremental encoders. So if the batteries go dead, then we lose the origin. If we lost the origin, then the robot does not what? Doesn't know where it's at. Are we okay? Yes or no? So we have an incremental encoder over there on the manufacturing line. Next class, what we'll do is we'll hook a scope up to it and we'll see it gives us this exact thing, same thing. So what does this tell us? Unfortunately, I can't reverse the animation, but if I reverse this up here, then what would happen? Now, what could happen? Either the sensors could be stationary and the encoder wheel could move, or the encoder could be stationary and the sensors could move. The most popular way on robotics is to move the wheel and keep the sensor stationary, because the sensors have to be powered up, right? But if you look at your print head, it's got all those flexible wires going up there anyway. Limit switches, everybody okay with those guys? Any problems there? Did we look at all? These are just different types of operators, or some people call them actuators. So something has to actuate the switch. We have two basic types of limit switches. We have what we call a plunger type, and then we have a rotary type. So this would be a rotary type. This is right here is the operator. So the limit switch don't make contact with anything. It's the operator that makes contact with something. So this is just a whip. This is just what we call a whip. It's got a spring back there so it will flex and not break.
Oh.
Yeah, that's what it is. It's just a whip. No, it's not. But this is an operator. This is an operator for a plunger limit switch. Anything that moves across, we're going to knock it over, or we're going to put some type of wheel out there to reduce friction.
You said spring.
Yeah. These are electronic duty or light duty limit switches. These are what's on our manufacturing. So all the ones we have over there are either this type right here, which just has a little lever, or it's the type with a roller. Of course, the roller, and we do have the plunger type. We have this type over there. And let's go over and do that before let's go look at them real quick before.